Hello, welcome to Unit 2, Lesson 1. This lesson is going to cover transformations on quadratics. And because for this particular sequence of lessons in the curriculum, it's the first lesson that we are really diving into the transformations. It is going to be a little bit long and very detailed at the beginning. So for those of you in my class, definitely have your notebooks ready. Also have a piece of paper ready for the 8 practice problems. Now, that is obviously specifically for my students because as we go through this lesson, we're going to do some practice and that practice is going to be evaluated. If you are watching this lesson from another teacher, another school, whatever it might be, then obviously you need to do whatever is going to be best for you if you are watching this lesson. So without further ado, I wanted to start off by going over some vocabulary, and this is probably review, but for some of you it might be new or you've only encountered these words once or twice in passing. So we want to talk about what it is to be a parent function. The parent function is the simplest function in a family. So we got simplest function in a family. Now, right there, as soon as I do that, you might have some other questions. So as you're writing that down, you might say, well, what do you mean a family? A family of functions is what we're talking about. So if you think about most families, the people in the family are all different, but they might share certain inherited traits. So for example, I have my dad's nose. Like it or not, I have my dad's nose. I have inherited his nose. I look very much like my dad. So when we're talking about a family of functions, what we mean is a collection of functions that share certain key traits. Okay, and they can be certain points or a way that they behave when we graph them, or a way that we solve them. And so the parent function is the simplest function in that particular category. So for a quadratic, the simplest function in the family of quadratics is f of x is equal to x squared. So why that's key? The x squared is what makes something quadratic. Okay, that is the thing that makes it quadratic. If you don't see an x squared, it's not quadratic. If you see something higher than a squared, okay, on the exponent, so if you see an x cubed or an x to the fourth, not a quadratic. So when we're talking about quadratics, we're talking about there has to be an x squared, and there's no exponent higher than that. And I don't want to dive too much into the weeds with what it has to be to polynomial, but for now, that's what we're looking at. And so f of x is equal to x squared is literally as simple as we can make it and still have it be a quadratic. If the f of x really, really bugs you, you can write y equals x squared. That's not going to cause any problems or issues with you understanding the material or getting this content right. The parent graph is simply the graph of the parent function. So if I were to graph a quadratic, the parent function looks something like that. Now, I did not do that probably as well as I should have, because I drew it going below the origin. So it actually goes through the origin. There we go. That's better. And the name of that graph is parabola. Okay, so that is what is called a parabola. Some students will say parabola just as a kind of way to remember that it looks like a bowl, but the way we pronounce it is parabola with the accent on the the second symbol there. And parabolas all have that general shape, so they're all kind of rounded at the bottom and they get wider as they go up. So what they don't do, and what I have to take off points if a student does it, if a student draws the sides of the parabola being vertical and it's very clear that they are trying to draw them to be vertical, like they're not. A parabola does continue to get wider the further and further it goes out. So that is the parent function and the parent graph. And again, it's the simplest function that we have that is a quadratic. So this is the part of the lesson that I think is really kind of long, and it's a kind of a gigantic chart. So what I will do when I present this in class is I'm going to give my students a couple minutes to set this up in their notes. So we've got translate up, translate down, translate left, translate right. Reflect it over the x-axis, reflect it over the y-axis, vertical stretch and vertical compression, also known as dilations. And you can kind of dilate it two ways. Just like you can go up and down, you can like dilate it to stretch it out, or you can dilate it to like compress it together. Some of these transformations are more common than others. You're going to see them a lot more often. So if you need to pause the video right here to copy that down in your notebook, do what you need to do. Okay, so that's the beauty of a video. You can just take the time to do what you need. All right, hopefully I gave you a chance to do that if you needed to. I want to home in for a second on the word transform here. The title of the lesson was Transformations of Functions, and this is a vocab word that you will see, and you'll see it in the directions. The directions will say, describe the transformations, is what the directions are going to say. And so what you're being asked when you're being asked to describe the transformations or state the transformations is the stuff in this table. And every year that I've taught this, I will have some students that get to the directions, describe the transformations, and they will tell me like 15. Or they'll try to, I don't know what they try, but they're not doing this, okay? Like they're doing other stuff. So in the 3 columns, what I'd like to do is in the first one, give you like a generic notation for what the transformation would look like. In the middle one, that's a little bit wider, we'll expand it, like we'll write it out in words, and then I'll give you an example. So just for a refresher, this is our parent function. Okay, so y equals x squared. So to translate up, suppose I want to create a new function that's different from the old function. Now this is where that f of x, g of x notation comes in handy, because I've got like the original function, which we'll call f of x, and then just for function, and then we have the new function, which we'll call g, just because it's the next letter in the alphabet. So if I want to translate the function up, I would do f of x, and then outside the f of x, I would put a number of some sort. So I will just say, like, I guess we'll just say k, okay, for that. So that says f of x plus a. So if you're having trouble reading my handwriting, 1, I am really sorry, and 2, I'll read it out loud. So it's g of x equals f of x plus k. And what we're doing there is we are adding a number outside. And I'll just say add to outside. Usually it will be at the end of the function, but it doesn't have to be. So somebody could say k plus f of x. The key part of that is that it would be outside of the f of x. And as an example, it might look something like this: x squared plus 3. And what that would do is it would take our parent function and would translate or slide our parent function up 3 units. Now, translating down is going to be similar. So if I want to translate down, I would subtract. And we'll use a k there as well. So we're going down. And that is very intuitive. So to add, you would like, if you add, you'd go up. If you subtract, you go down. And we're going to say subtract. I'll just do sub. That doesn't really look like sub, does it? Not really. Sub from the outside. And I really apologize. I'm writing with my finger. I actually should have brought home my tablet. I can write better. Probably look better when I do it in class. So you subtract from the outside, and this might look something like this: x squared like minus 4, and that would slide it down. And again, it's outside. It's not necessarily at the end. So if you wanted to do that the other way around, it would be negative 4 plus x squared. And you might get thrown off because there's a plus sign in there, but you want to watch the sign on the number. So that's actually a negative 4 there. So we're doing a plus negative 4, and that would allow you to switch the order. So that's how you go up and down. Now, to translate to the left, this is where it is a little counterintuitive. To translate to the left, you're going to go inside the function. Okay, so you're not going to have f of x and plus or minus something. You're going to have f of x, and then what you're going to do is going to happen inside of the function. To translate to the left, you might think that that is going to be subtraction, but it's not. It's adding, and we're going to use an h there. So if you're having trouble reading that, again, I apologize. it is what it is. We have g of x equals f of, and then in the parentheses is x plus h. And we might say we add on the inside of the function. You're like, okay, well, that's great, but what does that look like? Give me an example. Well, I would love to give you an example. Look like something like this. X, and then you've got the x squared, but before you do the squaring, you would say do plus 2. And that would slide the graph to the left too. It is what we would call counterintuitive. So it's not what you expect. If you question whether I am telling you the truth, go ahead and hop onto Desmos and graph y equals x squared, and then graph y equals x plus 2 squared, and see what it looks like. All right, now to go right, we would subtract. So again, we kind of have that counterintuitive piece there. So to go right, we have g of x is equal to f of, and this would be x minus h. And again, that's backwards from what you might think it would be. You think, oh man, to make it to go right, I should be adding, but it's not. And we could go through this the long way. We could build a table, plug in the x values, look at the y values, and you can see that, yeah, this actually is the way that the graph moves when you start plugging in the numbers. And if any of my students want to go through that, let me know. Like, I will go through that with you if you want to feel good about this. All right, so to make it go right, we subtract on the inside. Whoops. And what does that look like? It looks something like that. And that would send the graph 5 units to the right. So again, I apologize for my handwriting. It's been a long time since I've done this. I've been working differently in class so far this year, but so that says sub SUB and the word inside. Now we get to a couple of reflections. So, and these are different. So reflecting over the x-axis, you can see my hand. So if this is your parabola, reflecting over the x-axis means the x-axis is the mirror, and so your parabola would do this, right? So from this shaped parabola to this shaped parabola, and what you're doing is you are, like my hands won't move that way, but you guys get the idea, like that. Now to do that, we use a negative. And the placement of the negative is out in front. And so literally what that does is it takes every y coordinate, the f of x, and that was positive and makes it negative. So positives and flips it down and makes it negative. Or if it was negative, it would flip it up and make it positive because it would flip the sign. So we would say that this is done with a negative outside. And if I just did a flip, it would look something like that. Y equals negative x squared. And that's going to flip it over. Now, reflecting over the y-axis. This is one of those things. It is a thing. Like, we can do it, but it's also with a parabola, not the most interesting thing. Because if you think of a parabola, if we went back a slide, which I can't do in the recording, it's symmetrical over the y-axis. So if you think of that as being like symmetrical over my nose, and then I like turn it around, it's gonna look exactly the same. Okay, because you're just flipping something that's already symmetrical. Now you can do problems where you slide it left and right, and then you do the reflection. And you can make it more interesting that way, but that typically is not where we start. It is done with a negative on the inside, though, for what it's worth. And so you can say negative inside, and it would be y equals, and then you'd have the negative on the inside. You're welcome to graph that, and I mean, it's going to look exactly the same as a regular problem. It's going to look exactly the same because of the squaring, because it's symmetrical. But not every function is. So when we get to some functions that are actually not symmetrical over the y-axis, then that transformation becomes more interesting. Now, stretching and compressing are these are what are called dilations. Okay. And so to stretch, I can take an elastic out of my hair. So if you look in the window here, so I got my elastic, we'll kind of make it wide, okay, like a circle. The stretch does this. So the stretch is like going to pull it up like this. And you notice in the little window there, when I do that, it makes my hair tie skinny. So sometimes people will describe the vertical stretch as making it skinny. And hopefully you can see that little visual there, like I'm stretching it, but I'm stretching it vertically and it's making it skinny. The way that we do that mathematically is we multiply the function f of x. And instead of putting like a verbal description there, I'm just going to say a is greater than 1, because the assumption is that if you just have y equals x squared, that there's a 1 in front of the x squared. That's y equals 1x squared. And so if the number is greater than 1, it's going to stretch it out. You could think of it as making the slope steeper. Okay, that's not a wrong way to think of it. It's a little bit rough around the edges, but that it went from being a gradual slope to a steeper slope because you're pulling it upward. And an example might be something like this: y equals 2x squared. The vertical compression, we're going to use the same little template there. G of x equals a f of x. But the difference is that I could say a is less than 1, and that is lazy, but probably more intuitive. Essentially, though, what we mean is 0 is less than a is less than 1. So when I say less than 1, I mean a positive number less than 1. Why? Because a negative number is going to flip it over. So as soon as you have a negative, it's actually going to do something different. So here's the compression. So here's my hair tie again. We'll center that right on my nose. A compression would be like pushing it down. And you'll notice that when that happens, my hair tie gets wide. So we're pushing that force, we're compressing it down, and it's making it wide. So a lot of people will think of the compression as making something wide or fat. You'll hear a lot of different ways people express that. And so that could be something like 1/2 x squared would be an example. So this slide, we've been on this slide for a long time. This is the absolute most intense notes piece of it. But again, we've got the vertical stretch makes it skinny, and then when we compress it, it makes it wide. There is such a thing as a horizontal stretch and a horizontal compression, in which case you would be doing this and pushing it in from the sides instead of up and down. They are not common to talk about, not in college algebra, not really anywhere. They are a thing that you can, it's just you put the a value on the inside of the function instead, but like this is more than enough. I think most of you are like, yeah, I'm good. You've already given me more than I wanted. So the rest of the lesson should go much faster. Thank you for your patience on that slide. So for some examples in practice, state the transformations. Again, note what the directions say. Okay, because it drives me crazy as a teacher when I see students get questions wrong because the student doesn't understand what the directions are. So state the transformations. You are being asked, like, does it go up? Does it go down? Left, right, flip, like stretch, compress. So you want to see what does it do. So we're starting with the quadratic function, and here's what we notice. As you're going left to right, so I will usually kind of look at these going from left to right. Oops, did not mean to do that. I clicked on the wrong thing. Okay. Inside the parentheses, I have a +1. Now, I am not able to flip back. In class, I can flip back to the slide before. I cannot do it when you're doing a recording. It's like messes with PowerPoint. But inside the parentheses, I am adding 2. And we know that what that does is adding 2 will send it to the left 2 units. I also see that outside, I am subtracting 3, and that will send it down 3 units. That is all you're supposed to do. So like now you can see a student that tells me 15, does not understand what the question is asking them for. You are not asked to graph it, although you can graph it, okay? You can do f of x equals x squared and then graph g of x and look to see where the graph goes. You are hearing my new cat. I don't know if you can hear her, but I had some cats that were like YouTube famous for crawling across me in videos. They recently passed away, and I do have a new one, and she doesn't know about recording videos yet, that she's supposed to stay out of the way. So if you see a beautiful orange 10-month-old kitten, that is who's running around. All right, on to the next. If you see a negative outside, that is going to flip or reflect over the x-axis. And now we have that inside. So adding 1 on the inside will send it left 1 unit. And that's it. Like when you come to the end, you don't have to say, there is no like stretch. There is no vertical. Like you don't have to tell me what there isn't there. Just tell me what is happening. On this last one, we see the 1/2. So that is the multiplying. And that number is less than 1. So that is a compression. And then I see a -1 outside of the x squaring. And so that would be down 1. And that's all there is to those problems. So that took me 3 minutes with doing the PowerPoint and explaining about the cat that you're hearing, possibly hearing in the background. So none of these should take a long time. When you're first doing them, you may need to go back and look at that chart, but hopefully this is something that will come much, much quicker. So let's go ahead and check out the, oh, look at that. Okay, so what I'm going to do is I'm going to erase this. If you are watching the video, you can rewind it if you need it. That's, again, the beauty of that. I didn't should have realized that that was going to come up there. Okay, so pause the video, and in your notebook, you just want to get a little bit of practice. You try to identify the transformations on these functions, and then you can unpause it, and we will check it together. All right, so here we go. If you are multiplying by a number and that number is greater than 1, it is going to stretch the parabola out. If you are adding a 2 on the inside of the squaring, that is going to send us left 2. And if you are adding 4 on the outside, that is going to send us up 4. If you have a negative out in front, that will flip over the x-axis, and adding a 2 will send us up 2. So hopefully that went pretty well. If it did not, just make a note of what your mistakes are. Common mistakes are getting the left and the right and the up and the down reverse. So students will see like a +2 and they'll automatically say, oh, it goes up 2. And you just got to notice where the +2 is. The other mistake is getting left and right backwards. So they'll see like +2 and they'll just say, oh, that's we're to the right 2 instead of left. So those are the common things that students get wrong when they're doing this, just something to keep an eye out for. All right, now this is like a little bit of a side way, but how can we also find the vertex? The way that we're looking at these parabolas is in something called vertex form because it shows you the vertex. There are several ways to do this, but I prefer building off what we just did. If you know the translations from the origin, then you know where the vertex is. And so this is how, like, I would tell students that are new to this to do this. If you have the function g of x equals x plus 2 all squared minus 3, you would say to yourself, okay, that moves left 2 and down 3. So we're literally building off of what we just did. Then do a quick sketch. If you say it goes left 2 and down 3, then that means the parabola moved there. And what you would do is you're moving the vertex of the parabola. Therefore, I can now see that the parabola has, the vertex of the parabola is at -2, -3. Now, when you look at the equation, the -3 is right there. Boom, there it is. Okay. The +2, because we know that goes left, you would flip the sign on it. But wait until you're comfortable seeing that to do it that way. Can you do it that way? Absolutely. And if you just gave me a whole bunch of problems to do, like just me to do, then I would definitely just get it from the equation. But I have been doing this for longer than anybody probably watching this video has been born. So don't do that until you're comfortable. It did not take me long to do that sketch. It took me in the ballpark of about 10 seconds to do a quick sketch of where that parabola went. And then I can clearly see, okay, that is, -1. There we go. -1, -2, and this is -1, -2, -3. So I can see where the points are. Right, a couple of additional examples. This right here is going to flip it over. That actually does not have any impact on the vertex at all. This means it goes left 1. And so here's my sketch. I'm going to time myself. Here we go. Left 1. I'm going to change colors, flip it over. And that sketch took me 8 seconds to do. Okay, 8 seconds to do on a computer screen. And now I can see the location of the vertex that is at -1, 0. So I went left 1 and I did not go up or down at all. On this one over here, we do have a compression, but that is not relevant to, that is an E compression, that is not relevant to the question being asked. And this will make it go down 1. So again, timing myself, here we go. 1 down, change this, and compression is going to make it look wide. And there's my vertex right there. So that was a little bit longer. That was like 12 seconds. Hey, you can do a quick sketch. Just like, where is this moving? Where does that put it? And so this is the point 0, -1. Do mind which is your X and which is your Y. Whenever students have points that are on the axes, that can tend to be an issue sometimes with the points that are on the axes. Okay, so you try some. So problems 3 and 4, pause the video if you need to, and tell me where the vertices of those parabolas are. Okay, so right here, just to keep reviewing, that 3, because it is greater than 1, is going to stretch. The +2 is going to send us left 2, and the +4 is going to send us up 4. So here goes the sketch. So we have left 2, up 1, 2, 3, 4, and this is going to end up being skinny because we stretched it out. But there's my vertex, and my vertex is at -2, +4. Right here, we have a flip over the x-axis. We are also going to stretch it out, so that's fun. Neither one of those actually affect this problem. No left or right, because there's no adding or subtracting inside the squaring. And then this is up 2. So here is my sketch, up 2. We're going to flip it over and make it skinny. But there's my, good grief. I don't know if you guys can see that or not. There's my vertex, and my vertex is at 0, 2. So hopefully that went pretty well. Okay, it might have taken you longer than it took me, and that's totally fine because I've done it before. You can always rewind this, kind of look at your work. Did you do a sketch? If you got the answers wrong and you did not do a sketch, then absolutely start doing a sketch as a middle step. Don't try to jump over that until you are consistently getting the problems right and you're identifying where the vertex is. Don't rush the process. There's no way to like get to where you want to go. That's like a shortcut. Just take your time. Take your time with that. All right, now you may also need to describe the transformations from a graph or a table. We're not going to spend too long on the graphs. Typically for this, you would be asked to identify left, right, up, down, and a flip. You would not necessarily be asked to just do a dilation. You might be asked like that it is stretched, but you would not be expected to come up with the specific number that was used to stretch it, okay? So on this one, the original function is f, okay? So you look at the black one, and then you look at the blue one, and all you're being asked, again, is describe transformations. So did it go left, right, up, down, flip? What did it do? This one went to the left, and it went to the left 1, 2, 3 units. And so all you would be asked is left 3. That's it. So don't overthink doing that from the graph. So just went left 3. Now from the table, this top one that you see came from the curriculum that we are currently using. The bottom one I did. And so there's 2 different ways you could see the table. You can see it with like one set of X's and essentially 2 sets of Y's. So what that really is it's one table like for the X or for the F, and then the table for G of X would have like -4, -2, 0, 2, and 36, 12, 4, 12. And what the manufacturers of the table, that's weird, did is they tried to save space by saying, listen, the X coordinates are the same, and it's only the Y coordinates that are different. So like we're going to save space, and we're just going to tack on the other row. Keep in mind that f of x and g of x are both y's, and that's where that function notation does come in handy, because it gives us a way to say, okay, we have one function, we're just going to name it f, and the other function, we're going to name it g, and you're not dealing with 2 different y's that look exactly the same. So as you're looking at that, the x values are staying the same, so there's no left or right going on, but the y values are different, and they're different by a consistent amount. If you look at the first y value for f, it's a 39, but in the same spot with the g, it is a 36. When f is 15, g is 12. When f is 7, g is 4. And then we get another 15 and 12. Okay. This is Henna. She's going to settle down next to me. That's good. So looking for the pattern there, g of x is equal to f of x minus 3. So if you take the f of x value and you subtract 3, you're getting the g of x value. And we know from the, like basically the content of the lesson, that that is going to send the parabola down 3. So if you are asked for the transformation, the answer would be down 3, because the y coordinates, you're subtracting 3 each time. This next part, if you look at the y coordinates are actually the same. So you've got like the 34, 23, 14, 7, and 2. If you don't know where I read that from, okay, I was just reading it from there. But the x coordinates are different. Okay, so let's like kind of sketch this out for a second. Okay, encouraging you to sketch stuff out. So it looks like we've got we'll put 0, 1, 2, and then -1, -2, -3, -4, -5. So with f of x, we're going to be sitting at -2. And with g, we're going to be down here at -5. And so as soon as you sketch it out, you can see, well, we went left 1, 2, 3. We went left 3. Now let's just see if that stays consistent. So with the next one, we'll just kind of come down here. If for F, X was 2, and then for G, it was -1. And once again, you can see we went left 1, 2, 3. And so this transformation is left 3. And notice the role of the number line. Most of us are visual learners. Most of us do well with pictures and diagrams more than we do with just like tables of numbers and functions. And so a great tool for you is like just put it on a number line and just look. And again, note the observation that the y values were the same. And so that's our tip off. Okay, well, let's look at the X values and look at how the X values change. All right, so you try some, pause the video right here and go ahead and try some. Just write down what the transformations are. Okay, so for this first one, remember F is the black function and we have the blue function. And this is where you just want to look carefully. You might say it's dilated, it's getting wider, but remember that parabolas get wider the further out you go from the vertex. And so that piece that you're looking at where it looks like G is wider than F, it's not because it was dilated, it's because you're further away from the vertex, which means that it will be wider. What you want to notice is that move of the vertex that was supposed to have been red. And it went up 1, 2, 3. And so your answer there should be up 3. For this one, we've got that dual roll there. And if you notice, 4 becomes -4. 1 turned into a -1. 0 stayed the same. And then 1 to -1. So that means that g of x is equal to f of x, except it's negative. I'll pause for a second just so you can let that sink in. And so what that is a flip over the x-axis. So up 3, flip over the x. And you might have said, oh, I think it went down 8 or down 2, but then you notice the pattern doesn't hold. So you're always looking for a pattern that holds. Last skill. We are almost done, I promise, is writing a function given the original function and the transformations. So I'm going to give you the original function is the f of x. Okay, so f of x, and you are being asked to write a new function that is going to take the first function and go right 1 and up 3. So to go right 1, so we'll call the new function g of x. To make a function go right 1, I subtract 1 from the inside. To make a function go up 3, I add 3 to the outside. And that is it. That is all you need to do. It's just going in the other direction. So instead of me giving you this and you telling me it goes right 1 and up 3, I'm telling you right 1 and up 3, and you're putting that information into the equation in the right spot. Reflecting over the x-axis, that means we're going to have a negative. Stretched by, oh, that should be by, by, oh, I hate it when I find stuff like that. By a factor of 2, that means you're going to multiply by 2. And left 3 means we have a plus 3 on the inside. It does not have an up or down, so we're not adding or subtracting anything outside that function. You just go straight through. Again, we're just switching the direction. For the last one, we are compressing it by a factor of 1/2. That just means you're going to multiply it by 1/2. To make it go left 2, we would say, or sorry, left 1, that would be x plus 1. And down 4 means we would subtract 4 on the outside. Typically, people will give you the transformations in that order. They don't have to, so somebody could say down 4 and then left 1 so that they're not going in the same order. But usually they are, so that can be something nice to just kind of remember when you're doing these problems. And last but not least, a couple of practice ones. So that is the end of the road. That is the last slide. Pause and you try to write a couple of functions of your own. All right, so here we go. G of x. We're going to reflect it over the x-axis. That's going to be a negative. And then we're going to go down 5, which means that we would have minus 5 on the outside. Stretch by a factor of 4. That means we're multiplying by a 4. Left 3 means we do x plus 3. We'll have a plus 3 on the inside. And up 1 means we would add 1 on the outside. For any of these, you are welcome to hop onto Desmos or your graphing utility of choice and check your answers. Typically on some tests, like on most tests from my class, you are allowed to use a graphing utility, so you can always go and kind of check what you're doing and see if your answer makes sense. So you might encounter a test where there's a non-calculator portion and you wouldn't be able to, but if you can practice it enough, you probably find that you don't need to. I'm not finding the need to go and like check my work right now. So I know this video was long. Mostly there was like 15 minutes on that one slide at the beginning. And for my students, you will have a homework assignment, and I hope this helped. Come and join us next time for lesson 2.